Okay. I think last time we had this small issue and we could not finish the section. That day, did we start on the digital electronics? I don't think so. Digital pattern. आपका करना
No,
पड़ेगा. Hmm?
no, sir.
No. So today we are going to learn about the digital electronics, some basic concepts, certain things that you have learned in level 4. And then we are going to gradually go into some new concept that you have not covered in the level 4. Yeah. So first of all, what's the difference between a digital electronics kit and an analog electronics circuit? Others. Mother, so you basic concept of analog digital electronic circuits.
Analog signals have a continuous variation and digital signals have discrete variations as ones and zeros.
Yes, very good. Navani, you are correct. So we have already learned about electronics about representing data. We talked about that in the very first day in our lecture. Then we said even electronics is divided into two different categories. The digital electronics and the analog electronics. Digital devices or digital electronic circuits represent data using discrete voltage levels, while the analog electronics devices represent information using continuous voltages. That means voltage ranges. Digital electronics again divided into combination logic circuits and sequential logic circuits. We'll talk about sequential and combination logic circuits later. So this is the scenario where we have digital and analog circuits. So what are the advantages of having a digital electronic circuit over analog electronic circuit? What are the advantages? There are more than one advantage, but can you tell one or two? What are the advantages of digital electronic circuits? Now, can you remember we learned about a way to add the voltages, right? What is the device that we use to add voltage? In the previous lectures, not a digital one, we learned about an analog component that is able to add voltages. What is that?
Op-amp.
Op-amp. Let's say you are building a computer using analog components. This is how it was done before the digital computers were made. So if you want to add two signals, what you can do is, so we are basically having a summing amplifier, right? We are in one and in two. And let's say we have feedback as well. So we might have a result like this one. Output is equal to in1 plus in2. That makes sense, right? By taking a suitable resistor ratio, you are able to add analog voltages. Does it make sense? We have already learned about this, right? Now we can use it as a calculator, but maybe not as a very simple calculator. Why? It can do only one thing, it can only add. So if you want to do a subtraction, then again you can have another op-amp or same op-amp but configured to be a differential amplifier. So that way you can subtract signals. Okay. So if you use this one as a calculator, what are the problems that we might face? For example, let's say I want to add 3 and 5 and get the result. Then how can I use this particular circuit to do this? How can I add 3 and 5 using the circuit? Prasad, what do you think? Can you think of a way to add these two numbers using this circuit and get the correct result? How can I do it? කොහොමද කරන්න පුළුවන් අපිට? Okay, how can we represent number 3 in analog circuits? There are many ways, but you can come up with a very simple way. Give me a possible way to represent numbers. How, for example, how do you represent number 3? We can represent number 3 using 3 volts. Okay, so if you want to represent number 5, what should we use? What voltage? What is the voltage level?
5 volts.
5 volts. Now you are on the correct track. Then how can we use this circuit to calculate the 3 plus 5? What should we do? Sam, what are they?
We should give a range about 8 volts.
Not give. That should be the expected output, right? So if you want to add, we add the first number here. How do we add the first number? By converting it to a suitable voltage. For example, rather than saying 3, we will use 3 volts. Rather than using number 5, because we can't put a number in the circuit, we will be using 5 volts. Now then this particular circuit do the addition and give us the answer in voltage. So if it is a summing amplifier, what will be the output? Assuming this is in this particular order. We have selected that resistance in this way. Then what will be the output voltage?
8 volts.
8 volts. So if you are getting 8 volts, what number does that represent? What is the number?
Eight.
You have 8 volts, that represents 8. So this is a very simple analog calculator. This calculator is able to add two numbers, right? Now in real scenario, there might be some small changes. For example, rather than directly giving 3 volts, you can have something like this. That is a variable resistor. And there's a voltmeter. This is your input. And this is your second input. Again, a variable resistor. With the voltmeter, so you can know how much volt you are inputting into. You have your analog adding circuit with the op-amp. And output you have. What should you have for the output? If you want to measure the result, if you want to get the result, what should you have here? Output one node.
A voltmeter.
Voltmeter, yes. So you adjust this up and down until you get the correct number. For the voltage that represents the number you want. For example, if you want to have 6 and say -2, you should have minus voltage, okay? Then you configure it until you get 6 volts in here, -2 volts in here. And what will be the value you are getting here?
Four volts.
4 volts. The summing amplifier can get negative values. There's no problem. You get 4 volts. So in a way, it is doing the addition. Similarly, if you can use the differential, you can use the different subtraction. You can do the integration and all these things you can do. But doing it like this have a big problem. Can you think what the problem is? Can
The
you
op-amp has maximum
Yeah, that can
synonymous
be
of
an issue. But in analog circuit, what they usually do is they take they can divide it by 10 or 20, 10 or 100 or 1000 like that. So when you are saying 6, it might be actually representing 600. If you want to add 600 and 200, you just input 6 volt and 2 volts. At the end, you multiply by 100. But you are in kind of like the correct path, but not exactly the same problem. One problem is now when you have 6 plus 2, what is the answer?
8.
8. One question I can right. Is it exactly 8 or something very close to 8? Is it like this or is it like this? Can this answer be something like 7.999 in mathematics? Let's say I'm talking about mathematics. Can it be something like 7.99 or 8.001? 6 plus 2?
In this case, it's exactly 8.
Yes. In mathematics, when you add 6 plus 2, it's exactly 8. It's not 7.99, right? But what can you say about this circuit? Can we guarantee we will always get the exact value? For example, there might be small noise happening here. Okay. Or when we say the voltmeter 6, it actually might be 5.999. It's too small to measure. Or there might be some small problem with the op amp. So the gain is not exactly the same for both inputs. Something like that. Or this voltmeter has a problem. Or there's resistance in this line. Right? Or with, as the op amp get hit, hot, its gain changes. Right? So all these things can happen. So you can't always get 8. You can get a rough value, but it might not be exactly the correct value. But in mathematics, you don't have something like that. You always have the exact values when you're doing addition. You don't have something like 8.001. It's 8. But this way of representing information doesn't exactly capture the idea. So that's why we are getting this kind of noise. Because when you say number 6, it's just a concept. It's an abstract concept. This is a physical property. 6 volt is a physical property. Something you can measure. Something you can create. 6 is just a concept. So when you are converting concept into this voltage, there can be some problems. How are you correctly going to do it? Because all the calculations is carried in this physical value over this physical value or physical property for 6 volt voltage. So when you're having a physical property manipulated, you will always get some problems like noise and degradation and all these things can happen. So it's not easy to do it. And the worst case scenario is, let's say you have very long calculation and one result goes back into the input of the other. So if you have a small error here, let's say instead of 4, you have 3.99, and in the next step you are multiplying by 10,000, your error get multiplied by 10,000. So small errors can or tend to propagate in analog circuits. So that's a big issue because we are converting an abstract concept for numbers into a physical property. And we are trying to do that calculation or the operation on that physical property. So it's not easy. If we can somehow keep this number in the abstract form itself, then we don't get any noise. So that's the first problem. Second problem is something closely related. That is when we're transmitting the signals, you can get quite a large amount of noise. Or in other words, you can clear the noise. Just let's say this is your original signal. You have a small amount of noise appearing here. So your result will be something like this. Now here you can't separate the original signal or filter out the noise. Why? We don't know which is the noise, which is the real signal. Maybe the actual signal itself is something like this. We don't know. Maybe you have an actual signal like this and you had a noise like this, so you end up with like this. Or maybe your original signal is already like this and no noise, and you end up with like this. We don't have a way of determining whether this signal is correct or not, or how much noise is correct. So when you're transmitting signals, you have this issue as well. So in analog circuits, processing and transmitting both have certain issues. But in the digital case, you have some fixed values. Say 3.5. So either you have 5 volts or either you have 0 volts. Let's say you are sending a 5 volt signal. You had a noise like this. So your end result becomes something like this. This is 5 volt. This is 0 volt. Now the recipient, if he knows the signal should be digital, he immediately understands this is noise. Why? This can take only 2 options, either 5 volts or 0 volts. And seems like this is very close to 5, and there's a small noise or wiggling up and down or small variation in this signal. So you can immediately understand the person who sent the signal actually sent the 5 volts, but there should have been some noise. That's why there are some small deviations. Therefore, when you are transmitting the signal using digital signals, they are very robust. They are very robust. You can easily transmit in long distances. Even if you get some noise, you are able to filter it out without much issue. You can't do it using analog signals because you don't know which one is the correct signal, which one is the noise. Okay. Is it clear?
Yes.
The same applies for the processing units. For example, you can have 5 volt is equal to 1 and 0 volt is equal to 0. Right? So let's say you are doing some addition. So when you add them up, maybe let's say open, you end up with a 5 volt. So you know this is a digital one. Or you may end up with 4.99, just like in our original analog case, because there might be some errors, some noise, or maybe some problem with the processing unit. But still, you know, there can be only 2 outputs, either 5 or 4.99. So this means the correct result should be 1. There's a small noise of 0.001. So when you are sending the data to the next level, you are considering it as 1 and sending 1 as the input. So whatever the noise or the problem occurred at this stage is eliminated, because it is again converted back to the original form. So processing also becomes much more robust. So you can build a very complicated circuits or algorithms using digital mnemonics. For example, you can ask the same number to multiply it in, let's say, 1 million times. 1 multiplied by 1 million times. Now in a digital world, it will give you the exact answer as well. Why? Every time you multiply, you might get a small error, but it automatically cancels out, and the next step again you still get a 1. But in analog circuit, if you can do it million times, even a small fluctuation will grow gradually until you end up with something different. So these are the main reasons we are using digital electronics in modern circuits. Now, of course, there are some advantages in analog electronics as well. So that's why we have analog digital converters and digital analog converters. We'll talk about that a little bit later. Now, when you're at level 4, when I was talking about digital electronics, I mentioned 1 is represented by 5 volt, 0 is represented by 0 volt. That's not exactly the case. Because just a moment ago, I mentioned if you have a small noise, the circuit is still able to identify the correct value regardless of the noise. How does it do it? Rather than giving an exact value level, you have a small range. So any fluctuation inside that range, they will put it in the same category. For example, usually you have 0 to 2 volt range for the logic 0. So even if you get 0.01 volt or if you get 1.2 volt, still we consider it as logic 0. The electronic component we consider it as a logic 0. So you can have a voltage fluctuation up to 2 volts, even a noise up to 2 volt. You can still recover the original signal. Similarly, you have a range from 3 volt to 5 volt with a logic 1. These are some standards. So this one is not exactly this correct standard. There are many different standards. For example, it's not actually 5 volt. You can have up to 5.5 volt like that. So that's one thing. You have voltage ranges, and these ranges can also differ. For example, most common logic ICs, like in the 4000 series or 74 series, use voltage levels between 0 and 5. Now I'm going to ask a question. Let's ask from Patum. Patum, are you there? No. Patum? Patum now. Prasad. Prasad. Okay, Prasad, I'm asking a question from you, okay? Now, computer processor, modern day digital computers, sorry, computer processors, CPU I'm talking about, are they, I'm talking about microprocessor, okay? Inside the computer, you have a CPU, the microprocessor. Are they analog or digital? Modern CPU processors, are they analog or digital? Prasad, we can't hear you, are you muted? Prasad? Unfortunately, I can't hear from Prasad. Let's ask from someone else. Sam, what about you?
Digital.
Digital. Now, what is the typical voltage for a computer CPU? Anyone?
23 volts.
Sorry?
23 volts. That is
23.
normal.
Harin, I didn't quite hear what you said.
23 volts.
23?
Yeah.
No, not that time. I'm talking about CPU. CPU usually work with less than 2 volts. Why? The reason is when you're using computers, give me a second. The reason is now when you're using a CPU, it tends to get hot, right? Higher the voltage you input into the CPU, hotter it gets, right? So we usually try to keep it cool by reducing the voltage. So the logic levels in a CPU is quite less, sometimes even around 1.7, something like that. So if you have a full supply of 1.7, you can't have a logic level of 5 volts, right? So inside the CPU, the logic levels are different, very small. Similarly, if you look at a CMOS circuit, then they can change up to 0 to 15 volts. And if you look at some of the old computer outputs, they can have output voltage from -12 to +12. And you might have heard there are some microcontrollers that work with 3.3 volts instead of 5 volts. Right? For example, there are many, just search the internet and you will find some digital ICs or logical controllers or microprocessors work with 5 volts, 0 to 5. While there's a considerable amount of microcontrollers that work with 3.3 volts. So logic, so voltage connecting to a certain logic level is not fixed. It depends on circumstances, right? For example, if you're connecting RS-232 port into a microcontroller, you can't directly connect it. Both of them are digital using the same protocol, but voltages are different. One is using plus 12 minus 12, while the microcontroller is using 0 to 5 volts. So you have to do a logic level shifting. So when you are talking about digital electronics, you have to be concerned about these differences as well. So when you're building a circuit, check whether you are using the same type of ICs. If you try to use a 3.3 microcontroller with a 5 volt different logic IC, it will not work. Right? So that's one thing. However, the abstract concept behind them is the same. So when you are building a Boolean algebra or a truth table or something, they don't care about the actual voltage level. They only care about whether it is true or false, whether it is a logic 0 or a logic 1. So whatever the circuits you are designing using gates and things like that, they will be the same whether you use 3.3 volt ICs or 5 volt ICs. Only thing is when you are really building it, you have to be concerned about power supply and whether you are using the same type of ICs, right? So that's another thing I wanted to mention. Right, these are very simple things, so I'm going to do fast. So these are two logic levels, 0 and 1. Then we come to the concept of a truth table. Now, digital electronics can be represented. Any digital electronic circuit can be represented using 3 different ways. One is you can represent it using the truth table. What is a truth table? Truth table represents all possible inputs, all possible input combinations, and output for each of these possible combinations. So it's large table showing what are the all possible ways you can give a different inputs. This first input is high, second input is low, third input is high again, or first is low, second is low, and third one is high, like that, all different combinations. And there's a column showing what will be the output for each of these combinations. There can be more than one combination, then there will be more than one output column. Usually you have only one. That's one way of representing. Another way of representing it is, so this is a simple logic circuit. You have only one input, so that means only two combinations, 0 or 1, and Q is the output, which is in this case same as the input. Another way you can represent a digital circuit is through the logic gate circuit, logic gate design. So you can have whatever you say. It can be drawn using logic gates. If you are building the circuit, you will be using this particular path. The gate ICs are there, so you can buy and build the gate IC. Third way of representing information in digital world is through Boolean algebra. So it's a mathematical representation. Now I mentioned in digital world we try to do some abstract kind of calculations. Therefore, we can convert whatever we want to do into mathematical expression. Right? And we can even apply some mathematical operations on this particular algebra. So that algebra is known as Boolean algebra. So that's the third way of building it. You can have truth tables, you can have Boolean algebra, or you can have a logic gate circuit. They can be interchanged. In fact, you will often need to convert one of these into another form. That is usually required. These are some of the gates. Not gate. So not gate basically invert your input. So this is the logic gate symbol for the not gate. This is the truth table. This is the Boolean expression, X bar. So all these three are equivalent. They are the same thing. They have the same meaning. Okay. Then you have the AND gate. In the AND gate, this is the truth table, Boolean expression, and the logic gate symbol. Now, NOT gate can only have a one input, but NAND gate can have more than two inputs. Right? It can't have one input. It need to have at least two, but it can have more than two. In that case, what do you expect the truth table to be? For example, let's say you have a AND gate with 3. So what can be the Boolean expression for this one? Make it a Boolean expression.
A dot B dot C.
A dot B dot C. If you want to get output as 1, what should happen to A, B, and C?
All should be equal 1.
Or should be equal to 1. Very good. So it can be expanded to 3 or 4 or any number of inputs. Then we also have the OR gate. Same scenario, you can have more than 2 inputs. In that case, the condition is if you have at least one input as 2, output will become true. If you have at least one input as 2, you can have more than one, but even at least one as 2, your output become true. Okay? That's the basic of OR gate. I'm quite sure you are familiar with these things. We have already done them in level 4 and the A levels so many times. This is the exclusive OR gate. Since it's exclusive, we show it by drawing a circle around the OR gate symbol in the Boolean expression. Right. If you have 3 input OR gate, what will be the output? So 3 input exclusive OR gate. Okay, what will be the output of this one?
One. Not 1. And by the way, I forgot to tell you about this truth table writing scenario. Now, usually, there's a particular order we write a truth table. Now, even if you interchange the rows, it's not going to change the content, but there's a standard way of writing it. The standard way is you start with 0, so it can be single 0, maybe 2 or 3 or 4, depending on how many inputs you have. Then you add 1 to the previous number to get the next row. So you add 1 to this one, you end up with something like this. Right? Then you add 1 to this one. Now you don't put the 2 here. Now this is a binary number, right? So instead of 2, 2 is written as 1, 0. And from here you add another one, you end up with 1, 1. 0. So like that, okay? So that order is important. So what is the input for this one? Window is higher. Make it a Should be 0.
Yes, earlier you said 1, now you said 0. Yes, 1 should be correct. It's 0. Next one.
1.
1. Tricky question. Third one.
1.
Make all the things same.
Oh,
Very good. Third one.
again, it's 1.
Okay.
I'm going
No,
to
it should be 0.
okay give him the
No, sir. Only if there's 1 is the output should be 1, right?
It should be 0. This one,
Again 1.
very good. So Sama is answering. Now let's ask from someone else. How do you determine if the output is 1 or 0? Now, Sama, you can't answer. We'll ask Prasad. Is your mic okay now? Prasad, unfortunately, I can't see you. I can see your mic is unmuted, but we are not. Yeah, at least I'm not able to hear anything. Fatum, are you there? Fatum,
Yes, sir.
you are back. I was wondering where you were. Fatum, so how do you
Yeah.
determine when the output is 1 and when the output is 0? What's the rule?
Uh, First, we can consider A and B, and the output can consider with C. It's one when only one input is 1, and when all inputs 1, also 1.
Okay, let's say this is another exclusive OR gate. You have 1, 2, 3, 4, 5 inputs. What should be the output here? Harini, what is your answer for this question?
One.
So Harini says it's 1. Sama, what is your solution?
0.
1.
0.
Sama says 0. Patum?
1.
We'll put B. Prasad, what about you? Prasad, හැමතිස්සෙම මට විතරද අනිත් පැයට එනවා. Okay, anyway, so we'll keep it like this. So the rule is this. If you have odd number of true values, output becomes 1. Thanks, Prasad. He's saying it's 1. If you have even number of true values, output becomes 0. So if you look carefully, you have only one true value here. It's odd number, so output becomes 1. Only one true here, output becomes 1. Two true values. This is an even number, so output becomes 0. One true value, output becomes 1. So here, how many true values are there?
3.
So,
3.
3. So what should be the output?
1.
1. So if you have more than one input in a exclusive OR gate, that's how you calculate the output. Okay? That will be easy for you to remember rather than memorizing the full gate table. Right. So sometimes we can combine other gates to create more gates. For example, by combining a NOT gate to the front of the NAND gate, you get a NAND gate. So that's only not a NAND. And the symbol is also similar because you can say there's a small circle. Now, whenever you have a circle, that usually represent as a not gate. Okay. So NAND gate is considered to be a universal gate. We'll come to that later. And remember, this is x dot y. The whole thing is inverted. There's a bar covering whole thing. It's not similar to x bar dot y bar. Okay. This is not equal to this. Okay. So this means first you take the AND operation and then you take the NOT operation. This says first you take the NOT operation and then you take the AND operation. So order matters, right? It's like in physics, in other mathematics. If you do this, you get one number. If you do this, you get a different number, right? Here the multiplication happens first, is that symmetry first. Similarly, you have to be careful about this one. In fact, you have a different law for this one. It's the Y bar for De Morgan's law. We cover that in a little bit later. Now, whenever you have a dot like this, that usually represent this is equal to AND gate plus a NOT gate. Similarly, you can have a NOT gate at the front as well. In some circuits, you might have seen something like this. So what does this mean? This means we have NOT gate here and then AND gate here. Right. So this dot in liquid state is at the NOT gate. Even in ICs, in some ICs datasheet, you will see something like this. So you have something like clear, dot. There will be another not saying reset. So this again represents there's a NOT gate in it, or it acts inversely to what we usually consider. Usually, when you consider true, you go to a high voltage, 5 volt or plus 12 or something like that. But in this case, to consider it to be true, you have to go to the low voltage because you have a NOT gate. Yeah? So that's something you may find in other circuit diagrams. Keep that in mind. Now, this NAND gate is considered to be a universal gate. What does it mean by universal gate? Universal means it can be applied to anything. Right? For example, when you look at a word like a universal phone charger, that means you can charge any phone with it. Right? So similarly, when you say universal gate, that means it can be used to create any other gate. Now here's an exercise for you. Now we have the NAND gate. I want to use one or more NAND gates to create a NOT gate. So the first question. Use one or more NAND gates to create a NOT gate. Can you quickly do it? Is everyone using a computer? Anyone joining with the phone or anything? I guess not. So if you use a computer, you can draw it in Paint, or even in a phone, you can find some drawing there. Then you can share the answer with me. Okay. Right. I'll give you 3 minutes. Quickly do it. කීදෙනෙක් ඉවර කළාද? How many of you have finished? Some, what about you? Finished? No? Harini, what about you?
So I took a photo and I'll share it.
Oh, sure. You will share it out, right? Oh, good. I think that is sound, right? Yes, you are correct. Harini, if your one is also the same, then you will be correct. Ah, okay, you have put it in the chat, right? See, I'm sorry. Oh, that's a bit too complicated, isn't it? What is Sakir වැඩි දෙක? So what you can do is something like this. A and B. This is Q. This is A dot P. By connecting them together and giving us a one input, you will be able to get. Sorry, this is you will be getting something like this. A dot A. Why? Because there's no B. B same as A. So A dot A becomes A. So this becomes A dot. Right? So you can just connect them and get the result. And similarly, now let me show the other gate. This is the NOR gate. This is another universal gate. Right? You can see the circuit symbol and the table, also the Boolean expression. In both these slides, you will see I have put two expressions for the Boolean expression. In here, I have said x dot y whole thing bar or inverted is equal to x bar plus y bar. This is known as the De Morgan's law. Similarly, you can see x plus y whole thing inverted is equal to x bar dot y bar. This is a very important result. This is known as the De Morgan's law. You can use it to simplify many other things. Okay? So now x plus y bar is equal to x bar plus y bar. And x plus y bar is equal to x bar dot y bar. So this is the De Morgan's law. Here's another question. Create an OR gate using only the NAND gates. Create an OR gate using only NAND gates. You can use one or more NAND gates. Another 3 minutes. You can give a try. And also finish, can share the screen. Okay. Create an OR gate using NAND gates only.
So the question is not clear. Excuse me, sir.
ඉඳලා කියවල බලන්න. ඉවර කරත් කවුරුත් ඉන්නවද?
So no gate එකද NAND gate එකකින් හදන්නේ?
O gate එක.
O gate.
O gate එක හදන්න තියෙන්නේ. නෝ එක හැදුවොත් ඔක මොන හරි කලෝ කරගන්න පුළුවන් නේ. කරලා ඉවරනේ ෂෙයා කරන්න. Can you also add the logical Boolean expression at different stages? Boolean expression එකත් ඔය අතරින් තැන් වලට දාන්නේ. එතකොට වඩා හොඳට ඔක පැහැදිලි වෙනවා. What about others? Atom? හරියට ආගෙත් පුළුවන් නම් logic expression ටික මැදින් දාන්න. Boolean expressions ටික. Right. Other person who's the other. This is Sama, right? Harini, what about you?
Same as.
Still doing. Okay, fine. Prasad. ප්‍රසාද් නැද්ද නැත්නම් තාම මයික් එකේ ප්‍රශ්නයක්ද? ප්‍රසාද් නෑ නේද? රතුන්
සමන් කලින් ෂෙයා කරා.
ආයෙ ඔයත් ෂෙයා කරේ. මම ෆොටෝ එකක් දැක්කා ඊට පස්සේ වන් නෝට් එකක් දැක්කා. ෆොටෝ එක මම හිතන්නේ හරිනිකේ. වන් නෝට් ඩ්‍රෝවින් එක සාමාගෙන නේද? ඒක ඔයාගේද?
ඔව් සර්.
හරි හරි. ඕක මම හිතන්නේ මම හරිනිකේ උදේ. Right, here's another one. Now this is going to be a little bit more tricky. Build an exclusive OR gate using only the NAND gates. Okay, build an exclusive OR gate using only the NAND gates. Okay, I will leave it as homework, right? You can give it a try when you have free time. Now remember, there are more than one way to do it. Some circuits will be simple, some can be little bit more complicated. Not complicated, larger compared to others, right? But anyway, you can build it. Okay, we'll move to the next section. Next, we are going to talk about converting one form of expressions of a circuit into another form. Now, I mentioned there are three different ways you can represent it. Digital knowledge system. One is the Boolean expression. Another one is the digital logic circuit itself. Third one is the truth table. Now, we normally need to convert one form into another. Why is that? That has to do with the way we usually design a circuit. What happens is first you usually have some kind of a problem with description, right? Some textual description. Right? Let's say you are building a printer. Then you have some textual description about when these LEDs indicate lights switch on. For example, let's say this is an error LED. You can say if the paper is present, but if it is jammed at sensor 1 and sensor 2 is not detecting the paper, indicate paper jam at let's say near the tone. Or you can have another error LED saying, okay, if the paper is not present here, then indicate this particular light. So like that, first you will have a textual description of your problem. That is the most common way we will see a problem. When we want to build a circuit to solve some practical problems, we don't usually get a mathematical expression or anything. What you get is some textual description. Then you have to convert this textual description into something easy to understand, some mathematical concept. So if you try to directly build a circuit based on the description, it is very hard. If it's a very simple problem, you might be able to do it. But if it's a complex system where you have multiple inputs and some complex logic, it becomes increasingly harder to build a circuit directly from the description. So you have to have several intermediate steps. The easiest way to convert your textual description into a mathematical form is to by the truth tables. Because in the truth table, you can say, okay, A, B, and C are the sensors. When the sensor is on and sensor B is off, indicate this light. When sensor B is off and sensor is also off, then indicate like this. So like that, you can fill the truth table. That's very easy. Now, once you have the truth table, you have to build the Boolean expression for it. Why is that? Again, if you want, you can build a circuit directly from the truth table. No problem. But it will be very large. Why? Sometimes you can simplify your truth table to a very simple circuit. There can be duplicate rows. Now, in truth table, there's no direct way of simplifying it. Right? Maybe you can use something like a K-map to a certain extent, but the easiest way would be to use some algebraic way to represent it. Now, to use the algebraic expression, first you need to have a Boolean representation. So, how to get the Boolean expression? So, for this, you have to convert truth table into Boolean expression. So when you have the Boolean expression, You can simplify it further and get a simplified Boolean expression. Now, once you have the simplified Boolean expression, from that you can build your logic circuit. You can build your whatever the logic circuit that you have with it. So those are the steps. So you start up with some textual description. Like this. You convert it to truth table. You convert the truth table into Boolean expression, and then the Boolean expression into a logic circuit. Right? So we can see there are different steps in this one. So you need to learn how to convert between them. So let's start by teaching you one way of doing it. So what we basically have is three different things. You have truth tables, you have Boolean expressions, and you have logic gate circuit. So you need to be able to convert between them. Now this is the circuit to Boolean expression. It's very straightforward. You start with inputs, put some names or variables for them like X, Y, A, B, C. And as you move through your circuit, you perform the required operation. For example, you have not gate, so X is turned into X bar. Here Y is directly connected to Y, no changes. Here you have O operation, so X bar plus Y. Straightforward. Here is another one, but remember, you may have to include parentheses to clear or clarify what it means. For example, if you don't have the parentheses, what's going to happen here? Make a වරහන් දෙපො නැත්නම් මොකද වෙන්නේ? If you don't have the parentheses, what will be the output of this expression?
First x bar dot x should be calculated.
Yeah, if you don't have the parentheses, this should be x bar dot into x plus y. So these will cancel out and you are only left with y. But when you have the parentheses, the output is different. You will have x bar y term in your expression. So why do we need the parentheses? Because here x plus y is a single term. It's the output of this one, single term. So that single term is multiplied by the x bar. So you can't break it into two separate x and y after this stage. So to emphasize it, you have to put parentheses. To emphasize it, you have to put parentheses. So that's how circuit to Boolean expression works. Now you may have to do the other way around as well. How to convert a Boolean expression into the circuit. Here we can convert the mathematical operations into logical gates. Each mathematical operation has a relevant gate representing that information, that operation. For example, negation is done to the NOT gate, AND operation is done to the AND gate, and O operation is done to the O gate. And remember, when you have a parenthesis, you have to be careful. You have to start from within the parenthesis and start solving, just like any other mathematical formula, in any other mathematical expression that you are solving. Here's an example. X bar dot x plus y. We start with this one, x bar. So you have x bar means you have to put a NOT gate. Then you have x, however, it's within the parenthesis. You have x plus 1. So you have to solve this x plus y first. You can't take the x out and solve it. You have to have this whole unit together, x plus 1. And now we have built these two terms. These two terms are connected using an AND operator. So we put a AND gate. So you can see we are starting from inside the expression, from the innermost parenthesis, and gradually building the expression. Each time we build the expression, you can connect them using the relevant logic gates. The next thing we are going to learn is how to convert a truth table into a circuit. So first, you have to know how many inputs are there. Now you have two inputs. The number of combinations you will get is equal to 2 to the power of number of inputs. If you have only one input, that means 2 to the power 1, which means only 2 rows. If you have 3 inputs, that means 2 to the power 3, which means you will need 8 rows. In this case, you have only 2 inputs, which means 2 to the power 2. So that means you need 4 rows. So you build the truth table with 4 rows. And you also need to identify what are the inputs and what are the outputs. Here it is clear the inputs are x and y, and q is the output. So you put them as the column headers. Then since we know that we need 4 rows, we fill it in the order that I have mentioned earlier, starting with 0 and gradually incrementing it one at a time. Then we apply the first row into the circuit. That means we look at the first row, then identify what should be the inputs for that given row. Here the first row means x is 0 and the y is 0. These two. So you put x0 and y0 and go through the circuit. So you can see this is 1, this is 0, so 1 plus 0, you end up with a 1. Put it like this. Then you go to the next row. Like that, you go through the circuit, applying a row at a time. And every time you apply a row, you can calculate the output and put it as the output, put it at the output column. So this is how you convert a circuit into the truth table. Right. Before going into the description about how to convert a truth table into the circuits, truth table into a Boolean expression, I want to know whether it is clear for you all.
Yes, sir.
Clear, okay.
Yes, sir.
Right. Now we are going to convert the truth table into a Boolean expression. So the first step is to identify what are the inputs and what are the outputs. Usually Q is reserved for the output. So here I did not mention which one is the output, but Q is the output. And we have 3 inputs, X, Y, and Z. Then we select the rows where output is 1. We select the rows where output is 1. We can see 3 rows have an output of 1. I have marked them in red. So that's the first step. Select the rows that have an output of 1 or output as true. Then for each of these rows, we are going to create an extra term called mean term. Right? Going to create a term called mean term. Since we have 3 rows with 2 outputs, we are going to create 3 mean terms. So how do we going to do it? We select one of the rows. It's a first row that has output as true. Here, this particular one, the first red colored row has an output of 1. Then we write the mean term as a multiplication or the AND operation of all the inputs. Here we have 3 inputs, so we write it x dot y dot z. So this is common to all the rows that has 2 output. You also get x dot y dot z, x dot y dot z. The difference is when you add this row, let's say you add this first row which has 2 output, you go through the values. for each of the inputs. If the input is a 0, you put a bar for that input or a negation. Here, x input has a 0, so that means you put a x bar. Y is a true value, it's a 1, so you don't put a bar. Z is again a 0, so that means you have to put a bar. So midterm for the first row is x bar dot y dot z bar. We repeat the same process for the remaining rows. Here, if you look at the second row, where we have the two outputs, x is a true value, y is a false value, z is a true value. So x dot y bar dot z. Same is applied for the third row. Like that, we go row after row until we get all the rows with two outputs. In this example, we have only 3 such cases. Now for the last step, we combine all the minterms using logical OR operation. We combine all the minterms using OR operation. So we can see there are 3 terms. This is the first one, second one, and third one. Same as them. And you connect them using OR operation. So this is your Boolean expression. So if you evaluate it, you will see this will reproduce the truth table. However, if you are going to build the circuit from the truth table, you may want to do an additional step. That additional step is simplifying this particular Boolean expression. Because most of the time, you will find you can simplify this expression. That means your circuit will become simplified itself. Complex Boolean expressions will give rise to complex circuits. Because each operation needs a gate. Each operation needs a gate. So complex operations, complex expressions create complex circuits. But if you can simplify it, certain terms will get cancelled out. Then you will have a very simple expression, which means your circuit will also become simple. So that's something to keep in mind. Okay, we'll talk about Boolean logic a little bit later. Now, what will happen if you have multiple outputs? Sometimes you have more than one output. Right? Sometimes when you have a machine that need to light a certain bulb and also make a sound. Then depending on conditions, you might have different combinations of output. Right? Then how to do it? Or there might be several indicators. Right? So depending on whatever sensor inputs, you might have to light those indicators in different patterns. Then how do we do it? We do it by simply separating this truth table into separate, different, simple ones. We basically consider each output as a separate truth table. So if you have 3 outputs, first output along with all the input is considered to be one truth table. Second output along with all the inputs is considered the second truth table. And the third output along all the inputs is considered the third truth table. Okay? So here we can see there are 2 outputs. So X, Y, and Q together is one truth table. X, Y, and R together, you get another truth table. So once you have it like this, then you can apply whatever the things that you have learned earlier into these truth tables. And if you are building a circuit with multiple outputs, what we usually do is you build one output like this, and you build the second output like this, and basically connect the inputs, connect the common inputs. You have X for the first circuit and X for the second circuit. They are the same X, right? This X is shared by both Q and R output. So you connect them, and you have one Y for both Q and R circuits. So select the Y and share it among the Y, and you build the circuit. Right? So that's a little bit about how to convert between different ways of representing information. Any questions? Anything you want to ask?
So අපි අර කානෝෆ් මැප් කියන යූස් කරනවද මේක? සිලබස්.
Yes, we can use Karma. I don't think I put it in. No, it's under the Boolean expression. So we'll come and discuss about it when we're talking about the Boolean expression and after that. I think you had the Karma map. No, in your textbook there was a printing error. The title was there, but I don't think the K map. Yeah, K map content was not there. There was some small issue with that. Let me give you another small exercise. Now let me just slide about Boolean algebra. First of all, just like in mathematics, you have precedence in Boolean algebra. That means the order which you have to perform the operations. Now in mathematics also you have an operation order, right? You have to do the multiplication first before the addition. Right? You can't add first and then do the multiplication. If they are in the same line without any parentheses, you have to do the multiplication first. So that is called precedence. And in Boolean algebra also you have the same scenario. So the first one, the one with the highest priority, the one we need to do at the very beginning is the parenthesis. Right? If you have parentheses, first you have to simplify it inside the parentheses. Second one is the negation. Third one is the AND operation. Fourth one is the OR operation. So this is the order or the precedence of Boolean algebra. So keep that in mind. And here I'm going to show you some laws in Boolean algebra. Most of them are very straightforward, or you can say natural, right? There are only one or two that seems a little bit odd. Other than that, I think we should be okay with it. For example, if you look at associativity, that means if you add y and z together and then you add to x, it is same as adding x and y together and adding the z. In Boolean algebra, you can say if you take y and z, the operation of y and z, and then take the operation of x, that is same as taking the operation of x and y and taking the operation of the result with z. So that the way, the order you do it doesn't matter when you have all the instance associated of operation. Similar thing goes for the AND operation. And you have the commutativity. That means x plus y is equal to y plus x. X or y is equal to y or x. You have the identity. X or false is equal to x. And x and true is equal to x. Some of these things are very straightforward. Right. Can you quickly do these three things and put the result into the chat? Very good. Right. So let's move to the next slide. There are some other tools as well. Now these ones include two input, two inputs, two operands. The first two will be very straightforward. But the two absorption laws may not be very straightforward for some of you. So x dot x plus y is equal to x, x plus x plus y is equal to x. Those are the two absorption rules. And then we have the De Morgan's law and some other rules as well. So here are some few more exercises for you to try. Give a try for this one as well. If you want, you can take a screenshot of this one. If you can't remember these things, I think these two and these two are the only things that you may have to remember. Other things are more or less like the standard mathematics one. It should be very straightforward when you see it. And then try to solve these three questions. And again, put the answer in the chat box. Okay, now the third one, I think everyone is having a small problem. It's not a complicated one, but I think you are making it too complicated. That's why you are getting a wrong answer. So if you look carefully, what is this term? That is AB, right? What is the term next to it? May term with AB, na may term with positive term with one.
Together it becomes one.
Together it becomes one. So what is this term or this operation? Other operations. This one, and this one. What are they? They are O operators, right? So if you have one O, several other terms, what should be the result?
One.
It should
One.
be one, right? So you don't have to evaluate this rest of the terms. If you manage to note these two terms, you can immediately write it as one. Okay. There's another important property in Boolean algebra that is called the duality. So it's a kind of like a symmetry. Okay? What do you mean by symmetry? If you change AND operators with O operators and interchange true values by false and false by true, they still remain the same. Same means that they still remain true. Both of these things are kind of like same thing representation two different ways. Okay? So that is what duality means. So that's simply basic, simply things about the Boolean algebra expression. So now, since we have learned some basics of Boolean algebra, let's move to our main topic, which is about learning some other content. Now, we can use Boolean algebra to simplify it, but there are some standard circuits as well. So we will be learning about things like there are two types of combination, two types of circuits. One set of circuits are standard circuits. That means everyone knows what that circuit does. It has a standard name and a standard circuit diagram. So there are some circuits like that, like full ladder, shifters, counters, like that. There can be other circuits that are custom. For example, client or a person might come and say, okay, I want to build a circuit to do this. Now, there will not be any standard circuit for this. Right? Then you have to build your own circuit. So there are two different things. You have to know the standard circuits and you have to also know how to build a custom circuit as well. So first, we'll start with the description between the combination and sequential logic circuits. Because from this point onward, we will be designing and building circuits. Now, anyone know the difference between combination and sequential circuits? What's the difference? Don't look at the slide. Without looking at the slide, can you explain?
Sequential circuits take as previous states as well as present states as their memory, and they give the output according to them.
Exactly. In the sequential circuits, we can't directly say what the output would be. There can be certain cases, same input, but output differs. Right? Because depending on the previous scenario, the result will differ. In the combination circuit, it's not like that. If you give the input, the exact output will always come. It doesn't depend on the previous scenario. Okay? So we will first start by combination logic circuits. We'll first start with the adder circuit. Now this is a simple adder. So in digital electronics, numbers are represented using binary, just like all the other information. And if you want to add two numbers, you have to do binary addition. This is what a binary addition looks like. You can see when you have 1 plus 1, you get 1 0. Right? All the other cases, you have only single digit, so a single bit, 0 or 1. But for the sake of keeping the standard, you put a 0 at the front. So x and y are the two numbers. So 0 plus 0, you should have 0, 0, 0, 1, 0, 1, and 1, 0. So this extra one would actually be carried to the next binary points. It is similar to when you have decimal addition, 5 plus 7. You have 12. So we usually put the 2 here and carry the 1 to the next line. Right? Similar. So this is the standard circuit of a half adder. Half adder means you are able to add two numbers and get the result as in the previous truth table. But we have a small issue with the half adder. If you want to add multiple numbers represented in binary, half adder is not sufficient. Why is that? Let me screen and explain. Let's see if I have some number like this 101, and to it you are adding this particular number. Now here you are adding just two numbers, no issue, only 2. This one is only 2. This one is only 2. This one, when you add it, you will put a 0 here and you have 1 carrying out to the next place, right? So now you are adding actually 3 numbers, 2 from the original and 1 taken from the previous value. So in this case, it happened to be happen at this particular location, but we don't know when it will happen. For example, if you had 1 1 here or 1 1 here, then 1 will be carried into this location. So only place we can say for sure there won't be a carry is the carrying will be the last bit. Right? If you have something like this, you can see the last bit doesn't have any carry bit coming from here. So that one you can use a half adder. But for the remaining ones, you have a small issue because you are not only actually adding 2 bits, you are actually adding 3 bits. 2 from the original numbers, let's say A and B, and another bit that may come from the previous addition. So half adder is not sufficient for this scenario because half adder, you have only 2 inputs. But we need A, B, and another input coming from the previous addition, which is the carry in. So how can we do it? If we are to, let's say, add 3 numbers, one thing we can do is we can first add these 2 numbers together, take the result, and then add these 2 together, the result and this one, and get the final result. So it's basically doing the addition 2 different times, two times to get the final result. So a circuit that is able to do this one, that means a circuit that is able to add 3 bits is called a full adder. There are again many ways you can design a full adder. The one I explained now is one way of doing it. That means you can have 2 half adders connected together to function as a full adder. So this one at the first 2 bits, this one at the result and this next bit, and you get the result from here. So this is known as the full adder. So using full adder, you are able to add multiple numbers. Here, you will be able to see a full adder circuit that is designed to add 2 4-bit numbers. Right? You can see for the first, for the least significant bit, this one is called the least significant bit. This side is called the most significant bit. Least means it has the least value. Right? This one has the most significant or the most highest value. Right? In case of decimal, you have 1 place, 10th place, 100th place, like that. So for the least significant bit, you can use a half adder, but after that, you have to use full adders. You can see there are carry out coming into the carry in of the next line. So that is the addition of the numbers. Okay, it's 3:45. So before winding up to this lecture, I want you to try something. There's a free software called Lec5. So next day, download this software. Let me put it in the chat. This is the Lec5 software. There's another version called Lec5 Evolution, which is the new version. So you can use either of them. Old one called Lec5 or the Lec5 Evolution. So download this one because we will be using this to build some circuits. even the service that you learned today, you can build using it very easy. You can go to the gates. Let's say you are building a half adder. Select the gate, drag it, click it, and then you have some properties. Now this has 5 inputs. I only need 2 inputs for my circuit and gate. And I also need the exclusive OR gate. Put it there. Number of inputs is 2. And I want to have inputs. So these are my inputs. I can easily connect them. Always it's easily connected. Sometimes you have to make a little bit of fine root with the circuit. And to show the output, you can use this output port. And the output here. And then you can run the program. You can see when you click it, the values change. So you can see it's very easy. So from the next day onward, we will be using Lec5 to simulate some of the logic circuits. You can use Proteus for this, yes, of course. But it's, I think, sometimes a little bit too complicated for digital logic simulation. So this will be a little bit more easier for you to understand. If you want, you can use the Proteus as well. And this is free, right? So that's it for today. So download the Lec5 and try practicing the sum of the circuits we did today. We only did the full adder, half adder. But next day we will be using the encoder and decoder, things like that. Any questions you want to ask from today?